Today's session is about an introduction to deep learning using TensorFlow and Keras. We know that deep learning has taken the world by storm, and machine learning it has augmented, or it has enhanced the capabilities of traditional machine learning techniques, and it has enabled us to solve a much complex gamut of problems. Now, before we get on to deep learning, let's take a little introduction about a few terms around deep learning. Okay, so let us first understand that relation between three important terms: artificial intelligence, machine learning, and deep learning. Now, artificial intelligence, research on artificial intelligence, basically in terms of our ability to solve very complex problems and creating machines that are nearer to natural intelligence, which is animal intelligence and human intelligence. So research on that is going on since a long time, since the 30s and 40s and 50s. I mean, especially the 50s. Since the 50s, research on artificial intelligence have taken a upswing. Machine learning is a subset of artificial intelligence, various artificial intelligence techniques, which are mostly about looking at data, studying data, a machine studying data, and ability to recognize patterns within the data to perform complex challenges. And deep learning is again a subset of machine learning. Again, the commonality between machine learning and deep learning is that deep learning is also all about looking at data, historical data, and learning patterns from the data to solve complex problems. So these are some of the kind of relationship between AI and ML and deep learning, and we know that this question comes up quite frequently. We said that deep learning is a subset of machine learning. How deep learning is different than other techniques of machine learning is that the architecture of deep learning algorithms are impressed from the architecture of neurons in human brains, in terms of stacking of creation of plethora of neurons and stacking of neurons, just like human brains. Now, this analogy is given quite commonly at the beginning of training of deep learning algorithms. However, among researchers of deep learning, there is a debate in terms of whether this analogy is really correct or not. Now, this analogy is probably something that can be taken at the beginning of somebody's learning to understand deep learning. However, as understanding grows and person goes deeper into complex architectures and connections, and there are various complex elements of deep learning, maybe the analogy fades out. But for a starting point, this analogy probably holds good, and we will see how that is true. One other thing I wanted to mention at the onset is that the difference between classical programming and machine learning. Now, classical programming, such as you write a monolithic program to do a business task or functional task using Python or Java, or say, for instance, you develop an application using languages or frameworks like Angular, using various frameworks of JavaScript or React, etc., or say use C++, and you have a plethora of choices available there. So in classical programming, what happens is that somebody comes up, say your business comes up and says that I want this done, I want this automated. When that requirement is given to you, you know that what rules are to be implemented using your classical programming, what program you are going to write using the Java language, let's say. Yeah, so what rules you are going to implement in your Java program. Now that's pretty obvious in classical programming, that input is the rules, you know the rules, you encode the rules in your program, rules are encoded in the program, then that program is fed data and the program gives you answers. However, in machine learning, that includes deep learning, it's different. You don't write programs, you don't write business rules to automate certain predetermined tasks. In case of classical programming, it is deterministic. Rules are known well in advance. You know exact specific rules that are encoded. In case of machine learning, what you want to do is you want to solve some problems by looking at the data, by finding patterns in the data, recognizing patterns. You want to solve some complex problem. So your input here to machine learning, which is machine learning algorithms, is data and answers. So you tell the machine or your machine learning algorithm, this is my data and the data has questions, and I am also giving you the answers. So data is your independent variables or predictor variables, and answers are your target variables or the target variables or response variable. And when you feed the data and answers, both are data actually, the machine learning algorithm studies the data and the corresponding answers and creates rules, right? So it flips a little bit from classical programming. Okay, so that's a difference. Now we were talking about the analogy of neural networks with human brain. Now for that, let's understand the construct of the neurons in the human brain. I am by no means have any connection with medical science, nor do I understand the construct of human brains. However, for understanding the analogy, this is what we understand, this is what we have learned, which is probably enough to kind of understand the analogy. So human brain is created or comprised of millions and millions of neurons, and the neurons look like this. Two key components which are having which can be used for drawing analogy with our artificial neural networks is the dendrite part of the neuron and the synapse part of the neuron. Now the dendrites are the receptors and the synapse part are the connectors to other neurons. Okay, so this is the route, or this is the direction through which signals or input signals come into a neuron in human brain, and it passes through the length of the neuron, and it gets connected, and the signals are passed on to other neurons through the synapses, right? So there are few elements here. One is neurons accept inputs. Inputs are in terms of electrical pulses or signals in our human brain, and it passes those signals into other neurons through connections. The connections are between the synapses of one neuron and dendrites of another neuron. Now what happens in between? It just doesn't take input and pass it just like that. It also does a little few things. In certain cases, certain neurons get fired up, and it amplifies the signal before it passes the signal to the next neuron. And in certain cases, the neuron subdues the signal before passing it to the next set of neurons. Okay, and these connections are not one-to-one connections. These connections are many-to-many connections. So there is not one neuron that is there is not one synapse that is from one neuron that is connected to one dendrite from one neuron. There are many synapses from many neurons connected to one dendrite of one neuron, and then likewise that neuron through its synapses are connected to many other neurons on the other end, and it creates a many-to-many relationship between the neurons, and between neurons, right? So it takes in inputs as signals, it amplifies or subdues the signal, and it passes to other neurons, and there are many neurons are connected to one neuron, and that one neuron is connected to many other neurons. Now this is the basic architecture of human brain that is analogous to artificial neural networks in our context. Now this is a good analogy for a starting understanding or starting appreciation of artificial neural networks that we are going to learn today. Okay. Now, some of the achievements that deep learning architectures have made over the last few years, research on deep neural network really took off in the last 20 years or so, and the investments have from a few millions have gone out to billions and billions of dollars by companies like Google's and Microsoft's and Nvidia. Every large company, every progressive company are investing very, very heavily in deep neural networks nowadays, and the research and the new tools and new architectures and new algorithms are coming up like anything. Every day you will find some new improvements on existing architectures. Right, so some of the brilliant achievements that deep neural networks have made are in terms of near human level image classification. So our ability, we have eyes, and that's an input channel, and signals from the eye that you, whatever we view in front of us, go to the brain, and it actually goes through the architecture of neurons, through dendrites, through synapses, through a series of neurons. It passes through, and in certain neurons get activated and amplified, the signals get amplified, and in certain bunches of neurons the signals get de-amplified or subdued. All right, so that actually means that certain sets of neurons are actually responsible for our visual sensation, right? So that is, I mean, not all the neurons are responsible for viewing things or our optical sensation or optical senses. It's only a bunch of neurons that are responsible for it, and those bunch of neurons actually amplify the signals that are coming through your eyes and going to those bunch of neurons. Okay, so in terms of using deep neural networks, we have achieved near human level image classification, near human level speech recognition, near human level handwriting transcription, improved machine translation from natural language to other natural languages, superhuman level game playing, including Go and chess and many other things, improved ad targeting. So all the ads that you are that you see on web pages on Google or Baidu or Bing are have AI engines behind them, deep neural network engines behind them, which are automatically targeting very, very relevant ads based on your search habits. Okay, search habits, timing, context, etc., etc. So it takes in a lot of parameters and runs complex deep neural engines and pushes those ads to you. Right, autonomous driving, you know that there have been huge improvements in terms of autonomous driving. Tesla is taking a lead on that, but there are lots of other companies who are really making inroads into autonomous driving. Right, so similarly, there are many other areas where deep neural networks have made huge strides and helped us solve very complex problems. We would see that deep neural networks are not very, very different. Some of the core foundational aspects of deep neural networks are derived from the traditional machine learning processes. So at the beginning, at the start, you have the input data, so also applicable for deep neural network, and we have learning algorithms. So learning algorithms it can be traditional machine learning algorithms like naive-Bayes algorithm, or a support vector machine algorithm, or a decision tree, or a random forest algorithm, or a logistic regression algorithms, which are traditional machine learning algorithms. So here in this case, in case of deep neural network, we probably say that, okay, we replace this part by a deep neural network architecture. Right, so in traditional machine learning, let's take a case of a linear regression algorithm. So it's a linear regression problems algorithm solve regression problems. So let's say, for instance, you have a property agency. This is a common example that is taken in case of linear regression. So typical case of a regression problem is that you have a let's say property agency. Okay, and for the last 10 years you have got loads and loads of data. Millions and millions of houses have been sold by your company. When a new property comes in for resale, you have to send an inspector physically to check the house, take the property, and provide a valuation, right? Now this is done based on the evaluators experience based on various parameters. Now all those parameters are also captured as data in your database, so they are already available, right? So properties like what is the square footage of the property, or how many levels are there, how many floors are there, how many garages are there, how many toilets are there, how many balconies are there. So based on all those properties, the price can be determined. So why don't you automate the whole process and employ a linear regression model, okay, created by a linear regression algorithm, which will create a model of the relationship between the house properties or the property attributes and the house price or the property price, right? So the house prices are your predictor variables like x1 and x2 and xn, etc. And y is the price. So essentially what your machine learning algorithm, your linear regression algorithm in this case, are doing is that creating a model like this, creating an equation like this, the equation between the target variable, which is the house price or the property price, and the property attributes, which are denoted as x1, x2, x3, x4, x5, etc., etc. At the end, your linear regression algorithm will study the data and create the equation, exact equation, that is the best fit in modeling the relationship between the predictor and the target variable. Right? Now in this case, what happens is that the learning process, your learning algorithm is, so this is the model equation, right? This is the model equation, okay? This is the target variable and x1, x2 are the predictor variables. So your learning process actually determines the equation. So that means that it is finding the value of these parameters, theta 0, theta 1, theta 2, theta n, right? So essentially it determines that theta 0 has to be 9.7, or theta 1 has to be 3, or theta 2 has to be 4, right? So your learning algorithm is determining or learning the parameter values. So this theta 0, theta 2, theta 1, theta 2, these are the model parameters, and these model parameters are learned by the learning algorithm, and that process also remains same in case of deep neural network, right? Now while the learning process goes on, there are a few elements that we need to that are important to understand, and that is also applicable to deep neural traditional machine learning algorithms, as it is applicable to deep neural networks as well. And these elements are the loss function, the optimizer, the learning rate, etc. So now, what is the loss function? Is that we say that the learning process learns the model parameter through the learning process from the data. Now what is the basis of that learning? How does it determine this optimum values of the model parameter? By using a loss parameter, loss function. Now loss function is a function which is normally minimized. So in case of a linear regression, the loss function is MSE, mean squared error. So essentially the learning process starts with a random set of values against theta 1, theta 0, theta 2, etc., etc., and it determines the resultant predictor value, and it determines what is the loss, and the loss is determined as the predicted value of the target variable and the actual value of the target variable. So the learning process uses the already existing available actual values of the target variable, okay, which is y. So that is a loss function. So and in case of linear regression, mean squared error is a loss function. So in case of different types of problems, we use different loss function, but loss function is something that we need to mention, normally mention in case of traditional machine learning algorithms also, and in case of deep neural network also. There are choices of different loss function based on scenarios, and that is one of the things that when you learn deep neural network in detail, you will be exposed to lots of different types of loss function and what loss function to be used in what kind of scenarios. The next thing is the optimizer. Optimizer is that we have seen the loss function. So the learning process determines the loss function, and the goal is to minimize the loss function and getting to the stage where the loss value, the difference between the predicted and the actual values of the target variable, is minimum. Okay, so it works on minimization of the loss function. Now, how does it get there? It gets there by an optimizing method. Okay, and in normal circumstances, in cases like linear regression, we use by default we use an optimizer called gradient descent. Okay, so we are not getting into gradient descent explanation, but the gradient descent is the most popular algorithm, and it is something that you any machine learning engineer or anybody who is in the profession of data science and machine learning should understand gradient descent very, very well. And there are different variants of gradient descent that we can use. There is batch gradient descent, there is mini batch gradient descent, there is stochastic gradient descent, and based on your scenario, one of them have to be selected. And the other thing is, which is important to the learning process, is the learning rate. The learning rate is when the gradient descent is optimizing the values of your parameters in the way to finding the most optimum value while moving towards the minimum value of the loss, determining the minimum value of the loss function. It has to take strides. It has to experiment by incrementing the value, or incrementing or decrementing, so that is adjusting the values of theta 0, theta 1, theta 2, etc., etc., the model parameters in the gradient descent approach. Now, the learning rate determines the quantum of the strides it takes each time in the gradient descent approach. Now, if the gradient descent, if the learning rate is a very small value, then each step the values of the model parameters move a little before calculating the loss value. Now, if that learning rate value is very little, there are going to be lots of steps, millions of steps before the optimum values of the model parameters can be reached, right? It may take a lot of time. However, so you can tweak the learning rate to make it a little bigger, but which is going to make the process faster, the learning process faster. However, the other risk of making the learning rate higher is that you may skip the global minima and get stuck in a local minima of the loss value. Okay, so we are not getting into that, but these are terms that are very important to understanding of machine learning, and that includes deep learning. And these are foundational terms or foundational concepts that are also applicable to deep learning. So I wanted to give you this appreciation before we get on to deep learning. One of the most important elements, of course, the most important element of deep learning or any machine learning process is the input, right? Now, the deep learning algorithms expect the input to be in certain format, and it expects the inputs to be in the format of tensors. Now, tensors are actually arrays, and in Python representation, tensors are represented through NumPy arrays, right? That is the most common representation of tensors. Now, tensors can have different shapes based on the type of input that you have for your machine learning algorithm. Yeah, based on the type of input that you are having for your deep neural network architecture or deep neural network algorithm, the tensor's shape can differ. A tensor can be a scalar value, which is a zero-dimensional tensor. It can be a vector. A vector is a tensor. Vectors are 1D tensors, 1D single-dimensional arrays. It can be a two-dimensional array, which is a two-dimensional tensor, which is a matrix. So let's say a 3x3 matrix, or a 4x4 matrix, or 4x7 matrix, something like that. So those are examples of two-dimensional tensors. And you can also have multi-dimensional, three-dimensional as multi-dimensional tensors, right? But essentially, your deep neural network will expect a tensor as an input. Okay. Now, what kind of inputs are represented through what kind of tensors? So let's understand that. Let's say, for instance, your deep neural network is about processing images, right? So your images are inputs to the deep neural network. So images are not stored as images in the network in computers. Images are stored as matrix of numbers. Images can be black and white images. In that case, there is going to be a 2D tensor with the height and width of the image. So that many number of pixels into that many number of pixels of the height and number of pixels of the width is going to be the dimension of the tensor for black and white images. And what is going to be the content of that matrix? The content of that matrix is going to be the grayscale values of each pixel in that image. Okay, so before you input an image into TensorFlow or your deep neural network, you have to convert your images into tensors, which are essentially NumPy arrays, and there are mechanisms of doing that. Very simple APIs are there. If your image is a colored image, then there is an addition of a third dimension. Okay, then there is going to be, so colors are comprised of red, green and blue combinations, right? So then there is going to be sets of, for each image it is going to have its width and height, but it is also going to have a depth dimension, which is the channel dimension, and there are going to be 3 such channels for each image, which are going to be one for red, one for green and one for blue. So it's going to be a 3D tensor. And again, there are going to be color scale values for, just like grayscale values for black and white images in 3D tensors. So in colored images, you will have color scale values. Now if you want to feed in a batch of images to your deep neural network, and most often when you are processing images, you are not going to pass on one image as an input. You are going to feed the network hundreds and thousands, probably millions of images to learn from, right? For learning, for let's say image classification. So in that case, there is another dimension, which is the number of images. So the batches of images, so you have the batch dimension, you have the channel dimension, you have the height dimension, you have the width dimension. So there are, it becomes a 4D tensor. Videos are also 4D tensors. Why are video 4D tensors? A video is not a video. Video is basically frames. Okay, a video is let's say a 1 minute video is probably comprised of say 20 frames. Okay, so 20 frames, or let's say 30 frames, 40 frames, something like that. So it's actually a batch of 40 images. So it's a 4D tensors. Now let's imagine you have a batch of videos. So your video is already a 4D tensor. So when you have a batch of videos, if you have a video classification task, then your videos are going to be 5D tensors, right? So this is how the tensors are kind of shaped, and this is the input that you need to process. So it's important to understand the shape and form of the input that you're feeding your deep neural network. So this is a representation. So what I said is that let's say this is an image, okay, and if you have a color image, then you have 3 channels. So essentially 3, one is red scale values, one is green scale values, one is blue scale values. So 3 images, 3 2x2 matrix. So that makes it a 3-dimensional matrix. So in this batch, you have 1 color image, 2 color images, 3 color images. Okay, so this essentially is a representation of a batch of 3 colored images, right? And a tensor, this is a 2D tensor, of course. This is not a 3D tensor. This is a 2D tensor, and the tensors are going to be represented like this. I mean, normal, as I said, that it's most common representation is NumPy arrays, and this is how they look like. Okay, so these are things. These are how your inputs are going to look like for a deep neural network. Right, a little bit on the construct of the deep neural network architecture. Not the architecture, rather the tools or the systems that are in work for on any deep neural network. We have GPUs and CPUs. So for normal traditional machine learning processes, CPU is enough. You don't need the GPU, and it will not use the GPU also. Then on GPUs, the GPUs are managed through low-level deep neural network libraries such as CUDA or CUDNN deep neural networks from NVIDIA. And NVIDIA GPUs are the most common GPUs at this moment that is used in the industry. Now, on top of the deep neural, low-level deep neural network library, and we don't have to get into this for application, for common applications of deep neural networks, we normally would deal with APIs like Keras. Now, in between deep neural network low-level libraries, we also have tensor management libraries. So we said that our inputs are in the form of tensors, and those tensors get processed through our deep neural networks, right? Now, your deep neural networks learn from the data using, or learn from the tensors using various mathematical and statistical methods, right? And there is a lot of raw tensor management operations that are involved, which are taken care of by libraries like TensorFlow by Google. Microsoft has its cognitive toolkit, cognitive neural toolkit, and there are scientific libraries such as Theano, etc., which are proficient in, or whose primary job is tensor management for all those statistical and mathematical computations for deep neural network operations. However, to abstract those tensor operations from the normal user of or normal developers of deep neural networks, there are APIs that are available. Most commonly used are Keras, but you have API libraries like PyTorch also, and there are other libraries that are coming up for specific purposes nowadays. We normally use Keras API libraries, and the example that we are going to see today is also based on Keras, which use. Now, Keras API can use either TensorFlow or Theano or CNTK. Google has developed a variant of Keras which is called TF Keras, and our example is based on TF Keras, which uses TensorFlow, Google TensorFlow at the background. We'll look into this slide first. We have seen the example of the linear regression algorithm, and how the linear regression algorithm finds a suitable linear regression equation for the predictor and to model a relationship between the predictor and target variables. Okay, so let's say, for instance, this is the representation of our linear equation, and x1, x2, x3, xn, 2xn are our predictor variables, right? So you can take the same house price prediction case, and x1, x2, xn, 2xn are the property attributes. Now the learning algorithm will learn the model parameters, which are w1, w2 to wn. So this is the equation that gets created. Now what happens in neural network is that it's a different architecture altogether. The neural network, a typical neural network, is comprised of layers. Okay, it's a layered architecture. And in layers, each layer, there are numerous neurons. Okay, so if you remember the analogy between the human brain and the artificial neural networks, so different neural networks are examples of artificial neural networks. So we have a layered architecture, and second, each layer is comprised of multiple neurons. Okay, and those neurons can be are also named as perceptrons. Okay, in artificial neural network terminology, these are called perceptrons. So these are individual perceptrons. So this is a layer. Now in this case we have a very simple example. We have an input layer. So essentially my input layer takes in the various dimensions of your input. So you have x1, you have x2, you have xn, and these inputs are getting into the network. It's basically the input layer is a pass-through layer, and it takes in the inputs from outside, and then it gets into a fully connected layer, which is also called the dense layer. It's also called a hidden layer. Now each neuron or each perceptron in a particular layer is comprised of a function which is like the linear regression equation that we have built, okay, which is a dot product, which is producing an output which is the combination of a dot product between the weights that are being learned by the neural network and the input dimension or input attribute that is passed on to that neural network, into that neuron. Okay, so by doing that, it learns through that equation. The neuron learns the model parameters, again the same way that the machine learning, the linear regression algorithm learns. However, it also adds another dimension on top of this equation, which is the combination, as I said, the combination of the dot product of the weights and the attributes plus a bias term as well. On top of that expression, it applies a step function. Okay, so we are not going to get into too much detail, but for initial understanding, on top of the of that expression, it applies a step function, which is also called an activation function. So each of these neurons is comprised of a step function that is applied on an expression which is the combination of the input, the transposed input vector, and the weight vector plus a bias term, which is not mentioned here, but plus a bias term, right? That is how each of the neurons are constructed. This is a simple neural network which has only one hidden layer, one input layer, and one output layer. But in case of deep neural network, so this is a shallow network. Okay, it's not a deep neural network, it's a shallow network, because there is only one neural network, one layer of artificial neurals or artificial perceptrons. In case of deep neural network, this gets compounded by a number of layers, each constructed in the similar fashion, right, with the same function, same type of function, same type of activation functions. I mean, more often same type of activation function. So when you add multiple layers, so it can go up to for solving very complex problems like video processing, image processing, it may go up to hundreds of layers, and the number of weight combinations can become literally into millions that the network has to learn. So thereby training of neural networks is also very time consuming sometimes, when the inputs, number of dimensions in the inputs are large, number of layers in the neural network are large, etc, etc. So it can become the learning process becomes very time consuming, but it can end up solving a lot of complex problems. Okay, and the output layer is also the construct of the output layer is dependent on the problem that you are solving. Now, what are the types of problems that you may be solving with your neural network? Just like traditional machine learning problems, the problems that traditional machine learning can solve, the deep neural network can also foundationally can solve the problems like binary classification or multi-level or multi-class classification or multi-level classification. It can solve prediction problems like regression problems like the house price prediction, etc, etc, but at a much complex degree. Okay, it can work very well with images, and there are different types of architectures of neural network, deep neural networks or neural networks. For instance, for image processing, there are convolutional neural network that has a different construct. It has operations which are slightly different, which are called convolutional operations or pooling operations, which then get fed into a construct like a traditional deep neural network construct like this to effectively or efficiently perform image processing tasks, right? So this is some of the foundational ideas about deep neural networks. So normally you will find input layers and then several layers of neural network, several hidden layers, and followed by an output layer. But in case of let's say convolutional layer, that has a different architecture. It has this convolutional layers, and it has pooling operations, etc., etc. So those are different. There are different kind of layers that you need to add before the dense layers, or before the fully connected layers, which are for which an example that we have seen. Or for instance, if you are doing natural language processing, then there are different kind of constructs that are available. You can have an encoder-decoder model. You can have a RNN, recurrent neural network, which is a foundational construct of encoder-decoder model. Or you can have complex constructs like LSTM, long short-term memory, where the entire construct and the mechanism of your cells are going to be vastly different than the simple one that I have explained here. Okay, so it has a layered architecture. There are different kind of network or deep neural network architecture based on based on problems that you are solving can be available. There are different loss functions. As I said, that loss functions can be MSE. So if you are solving a prediction problem or a regression problem, you can use MSE, and for traditional machine learning algorithms, and MSE can be used for solving similar problems for regression problems for with deep neural networks as well. But there are there can be different other loss functions. So let's say, for instance, you are performing a classification, solving a classification problem. So in those cases, you can use a binary cross entropy loss function, or a sparse categorical cross entropy loss function for multi-class classification problems. So there are choices of loss functions, and based on the scenario, you can choose your appropriate loss function while you architect your deep neural network. We spoke about gradient descent as one of the foundational optimizers that are used by some of the traditional machine learning algorithms. A deep neural network also uses gradient descent, stochastic gradient descent, batch gradient descent, etc. But apart from that, it can also use several other optimizers which are very effective, which adjust the momentum and the learning rate, etc., etc., to optimize the gradient descent. Those are built on top of the other optimizers are also based on gradient descent, but they tweak the learning rate and keep on adjusting the learning rate or the momentum, etc. So those are elements that it adjusts to make it more efficient than gradient descent. Then you have objective and step functions. So I said for your cells, on top of the equation, the traditional equation like a linear regression equation, you apply a step function, and there can be different choices of step function. So step function, like I said, there was an analogy between the artificial neural network and the human brain. I said that signals coming into neurons can get subdued or amplified. The same thing can happen for deep neural networks also, your neural networks also. So in your neuron or perceptron, in your artificial neural network, in your deep neural network, if you want your signals to be only amplified and not subdued in any of the cases, then you use and this is the most common of all the step function, you use something called ReLU, R-E-L-U, which stands for rectilinear units. So what happens is that signal coming in, only if there is a positive outcome from that particular cell or that particular perceptron or neuron, the ReLU will output the positive value, and in case it is outputting a negative value, it is going to convert that into a 0. So similarly, there are other step function or activation function or objective function. There are different names of the same thing. So based on various scenarios, you can use ReLU, LU. There are 10H functions. There are other functions that you can use. So these are all elements of architecting your deep neural network based on scenarios that you are or the problems that you are solving. So we have gone through some of this. So we have input, then there is a learning process, and then we spoke about learning rate and the loss function and the optimizer. So other optimizers can be RMS prop, SGD with momentum, etc., etc. Now we will look at a worked out example, which is a Python demo. What we are going to do in this example is that we are going to do a multi-class classification using images. All right. Now, the MNIST dataset is very famous for learning either machine learning or traditional machine learning algorithms, as well as deep learning algorithms. So in this case, what we are going to do is that we are going to use something called Fashion MNIST. Okay. Now, Fashion MNIST is a library of bunch of images of garments. Okay, it can be shirt, it can be coat, it can be jacket, it can be trousers, and etc., etc. Okay, so I'll give you a glimpse. They look like this. Okay, so it's a, let's say it's a hoodie, or this is a lady's top, or it's a shoe, it's a frock, and this is a shirt, or this is a t-shirt, or something like that. Okay, so it contains a whole bunch of images of garments. Okay, so to elaborate on the problem a little bit more, that our input has so many pictures. There's a bunch of 60,000 such images of garments, and the labels are also given. So we know from the input data set that which one is a coat and which one is a hoodie, or which one is a shoe, or which one is a sneaker, which one is a jacket, etc., etc. So your images are there and your labels are also there. So that's our input. With that, we are going to create a deep neural network, which is going to create a model which is going to help us, given a new image, classify what type of garment is it. Okay, so it's a typical image classification problem. Now, one disclaimer that I would give before going on to this example is that this is not the right way of image classification. The right way of image classification is using a convolutional neural network. But because this is an introductory workshop on deep neural network, we have taken this example and we are going to solve this problem by using a traditional deep neural network architecture. Okay, it's not going to be very deep. It's going to be a few layers, and it is not going to be. It's going to be a traditional neural network with dense layers, and not a convolutional neural network. Okay, so it's just for learning and demonstration. The first thing we are going to do is import a few libraries, which are we import the TensorFlow library, the NumPy library, the Pandas library, and the Matplotlib library, because we are going to plot some images as well, graphs as well. We are going to see later. And we definitely need Keras, and we also need optimizers from Keras. So we said that there are going to be optimizers that we are going to work on, and we will see. And those optimizers come from the Keras optimizers library. So the next thing that we do is that import our dataset. So the dataset is part of Keras library itself, Keras datasets library, and we import the library by using the load data function of the dataset. So there is a dataset object that we have created by this, and we are invoking the load data function, and it returns 4 datasets actually: xtrain full, xtrain, ytrain full, xtest, and ytest. So xtrain will actually hold all the images from the input, and ytrain are the corresponding labels. X test is the test set, and the Y test is the test set images, and the Y set is the corresponding labels. Okay, so the dataset is imported from the Keras datasets library. Now we check what is the shape of the tensors. So as I said that I kind of explained what kind of shape our tensors are going to have based on the type of data that they represent. So in this case, our data represent images, and images that are grayscale. Okay, so yeah, so images that are grayscale, black and white images, and we have 60,000 of them. All right, so 60,000 comma 28 by 28. So each image is of dimension 28 pixels by 28 pixels. So that's the dimension of each image, and we have 60,000 images, and there are 60,000 labels as well, corresponding labels as well. And for test set, we have 10,000 images, each again with the same dimension. Okay, now we will scale this data. Now I'm not sure how many of you have exposure to the scaling concept. So if you have, that's great. What we do is for gradient descent and for some other machine learning algorithms, it is recommended that we scale the data into an uniform scale. Okay, so that means that so before that we have to first understand how many dimensions our data has. Now each image has 28 by 28 dimensions. The values in each of these 28 by 28 number of dimensions are different. Okay, some pixels border are closer to the border, so most of them will have pixel values or grayscale values representing white. And then there are going to be sections of images which are going to have other values representing black. Okay, because where there are darker shades in the images, you will have different pixel values, right? So if there are bordering regions, then it'll be closer to white and will be having values closer to 255. The grayscale values range from 0 to 255. There are 256 numbers. Okay, 0 representing white and 255 representing black, right? Now based on where the pixels are, the values are going to differ. The scale of the values are going to differ. Now if the scale of the values differ, then gradient descent finds it difficult to optimize the model parameters. Okay, and hence it is recommended for gradient descent optimizers or gradient descent related based optimizers and some other optimizers as well to scale the values to the same scale. Okay, now in this case there are different methods available for scaling: standardization, normalization, etc., which can be done, which can be used by using libraries like scikit-learn. But in our case here, we are going to use a very simple and crude method just by dividing the image values by 255, the pixel values by 255 all across. Okay, after the scaling process is over, we create a set or an array, actually a list with the textual label names. Okay, so this represents 0 in the label, this represents trouser represents 1 in the label, pullover represents 2 in the label, and so on. Okay, so if you say y train of 0, that means the first label in the training data set, and that's a numeric value in our input, and that numeric value is 4 here. And when we return, when we access the class names list and pass on this value which is translating into 4, we get quote. So essentially this is a demonstration of how we can kind of determine the label later on. Individual images are of shape 28 by 28, and this is how the images look like, so let's not get into that. interpreting the images, and we took the pain of printing the images on our screen by using the IMShow, by taking each of the image tensors, and we've taken only 16 of them and printed them, okay, just for demonstration. And this is because this is the input that you are working with, okay. So this is from our training data, the first 16 images from our training data that we have printed. Now we create our model. Now we said that we are going to use the Keras API, and in this case we are going to create a sequential model. Now sequential model is the API layer in Keras, which helps us create sequentially stacked neural network architectures. And most of the deep neural network or neural network architectures are normally sequential. There are going to be different other architectures. When we go deeper later on, maybe in another session or in one of our programs, there are different other architectures. But in this case, and maybe in most cases for solving problems, we are going to use sequential architecture of neural networks. All right. So we say that we create a sequential model from using Keras API. Now we are going to have 3 layers in our neural network, okay, so represented by this command and this command and this command. So in each case what we are going to do is we just add the layer. It's as easy as invoking the add function on the model from the Keras API, saying that okay, add a dense layer which is going to have 300 neurons. We say that in deep neural network architecture you have each layer, and each layer are going to have multiple perceptrons or multiple neurons, okay. And in this particular case, so we have 300, the next one with 100, the next one with 10. Now the activation function is the step function that we explained before, which is ReLU, the rectilinear unit step function or activation function. There are a couple of other explanations. In our input layer, and this is the input layer, the first line is the input layer. What we are doing is that we are taking each image which are of dimension 28 by 28 pixels. We are saying flatten. Now why are we saying flatten? The flatten function is going to flatten these images into a vector or one-dimensional tensor of the number 28 by 28. I think it's 738 or something like that. All right, 738 or 784, something like that. Okay, so that's the number. So that is what is going to be input to our neural network, right? So it starts with a flattened layer. So it's a 1D tensor that is coming in. The first layer is going to have 300 neurons. The second layer is going to have 100 neurons. And the third layer is going to have 10 neurons. Why 10? Because there are 10 classes. We are solving a multi-class classification problem. In this case, there are 10 types of garments that we have in our image set. Okay, so what are the 10 types of garments? These are the 10 types of garments: t-shirt, top, trouser, pullover, dress, coat, etc., etc. So it's a multi-class classification problem. So our output layer should have 10 neurons, 10 output neurons, and the activation for multi-class classification problem is a softmax classification. The output actually will have a probability value for each of the 10 types of images. For each image, for each input image, the output will be a vector or a 1D tensor. The first one representing the model's predicted probability of that particular image being t-shirt. The second element in that tensor is going to be the probability from the model of the image being the input image being a trouser, and so on. How can we actually predict the final outcome that we want to have, which is which is actually the predicted level for that particular image, is by using a function called argmax, which we are going to see a little later. Okay, and we can invoke the model summary function, which is going to give you the specification of the architecture that you have created. So you have created 4 layers. So one is the input layer, which is a flat layer, followed by 2 hidden layers, 2 densely connected or fully connected layers. The first one having 300 neurons, the second one having 100 neurons, and the final output layer is comprising of 10 neurons, 10 output neurons. Now the next thing that we do is compile the model. Now while compiling the model, we provide several parameters or hyperparameters for the model. The first one is loss. We have spoken about loss, and for this particular case, which is a problem type of multi-class classification, normally a sparse categorical cross entropy loss function is used. For a binary classification problem, a binary cross entropy loss function is used, and for regression problems like house price prediction or a car price prediction type of problems, you can use a mean squared error MSE loss function. The optimizer in this case that we have used is SGD, stochastic gradient descent. That is the most used one, but there are better, not the most used ones, one of the conventionally used ones, but there are other better gradient descent based optimizers that you can use. One such is RMS prop, AutoGrad, etc., etc. And the matrix that we are going to observe in the model while training it is going to be accuracy, right? The accuracy as to what is the predicted level and what is the actual level from the training data and the validation data. So the next thing that we do is train the model by the model.fit. So this is same as your traditional machine learning models as well. In this case, we train using the XTrain, that is the training images set of 60,000 images, and Y-train the corresponding values. We run 10 epochs. I'm going to come to epochs. What is epochs in a bit. Batch size of 128 and validation data. Take it from X valid and Y valid. Okay, which are our test data. Now there's a little bit of explanation required on what is batch size and what are epochs. Epochs are iterations of training that the model goes through, and each time in each epoch it trains with the entire data set, and the batch size determines as to during each epoch what is the size of the batch of images that it should feed in each iteration within the epochs. Okay, so if there are 60,000 training images and our batch size is 128, in each epoch the number of iterations of trainings that the model is going to go through is 60,000 divided by 128. So that many number of iterations within each epoch, and then continue this process 10 times. What happens after each epoch is that the average loss value, the average accuracy value, the average validation loss, and the validation accuracy values are calculated from the entire epoch after running iterations with batch sizes of 120, exhausting the entire training data set. These values are calculated at the end of each epoch and they are printed. Okay, so this is what you get. So you see that loss values are gradually decreasing and accuracy values are gradually increasing. And it can also be, I mean, we have run with 10 epochs, but it can also be that if I run it for 100 epochs, expecting that we are going to achieve even more accuracy, it may not be true. It may not be true because it may start overfitting. So when it starts overfitting, then the loss values are going to continuously decrease, or accuracy values will continuously increase, but your validation accuracy and validation loss are going to go lopsided. Your accuracy, validation accuracy will start diminishing, and your validation loss and your validation loss will start shooting up when your model starts overfitting because you have used too many number of epochs. Now there's a history object that is created by the model training process, and that history object keeps a track of all these values from each of the epochs. So if you plot that, you see this is how it moves. So the validation, the training loss and the validation loss gradually comes down, and the training accuracy and the validation accuracy kind of goes up, and they stabilize. Both of them, the loss and the loss here and the accuracy here for both training and validation, they kind of stabilize here, and they stabilize kind of around this epoch. So now from here you can actually take a guess that, okay, if I train the model with 4 epochs instead of 10 epochs, I will still get the maximum value. So why waste my training resources and also the risk the possibility of overfitting, right? So you determine, you can, I mean, from this plot you can determine your optimum number of epochs that you should train the model with. Okay, so now what you can do is similar to classification models using traditional machine learning algorithms. So you can do a test using sample images, and when you do that, it'll actually predict probabilities. Now why I have rounded off these values is because if I round it off, then it is going to show either 0 or 1. Okay, and where I have 1, that is the predicted level of that particular image. So what is the image level in case the last of the possible 10 values in the output vector or output tensor is 1? That label is, look at your class names, that label is ankle boot. So it's a little bit of trick. You round it off to find out the, get the predicted level. So this is an ankle boot. This is going to be probably coat or something like that, hoodie or something. Yeah. So these are your predicted levels, and this is called a sparse matrix, right? And looking at the position of the 1, you have to find out the predicted level, and you can actually guess the number by using the argmax function. So if you feed that into the argmax function, it actually gives you the number level. Okay, so in case this in the 10th position, it returns you 9. So basically the 10th category between the numbers 0 and 9, right? Okay, and you can do the prediction using the same old model.predict using the input image or input data, similar to what you can do with other traditional classification algorithms in machine learning, right? Here is a little bit of demonstration of the predicted class levels, and the second one are the predicted class levels, and the first ones are the actual class levels from your test data set. And after prediction, we have printed this. So you see that sandal sneaker, this is wrongly done. Sandal ankle boot, this is wrongly done. Trouser is correctly done. T-shirt is correctly done. Mostly rightly done, but there are some mistakes as well. Yeah, like this. Sandal classified as sneaker wrongly, sandal classified as ankle boot wrongly, etc. Okay, maybe these mistakes are not going to happen when you solve the same problem of multi-class classification, image classification using a convolutional neural network, because that is specifically for image recognition. Okay, and with this you can also apply a confusion matrix, and you can find out print a confusion matrix similar way you can use in traditional machine learning methods, and you can also use your print your classification matrix, right? So we have an average score of about 80%, which is decent, but this is for demonstration of a simple image classification using a traditional or conventional deep neural network. But again, not an ideal solution for image classification, for which you have to use convolutional neural networks. But for learning purpose, for starters of deep neural networks, this is a perfect example. With this, we come to the end of the session on introduction to deep neural network using TensorFlow and Keras. Thank you.